Oh, look, thanks very much. I'm just trying to figure out how to get my computer to share the screen here at this point. Wants to quit and reopen. Okay.
Should be top right-hand corner next to the leave button.
Yeah, no, I had to change some permissions. I'm going to be back in a second.
Okay. Might be to the release on that.
Look, so what I was actually planning on doing was doing this more as a Q&A, given that I'm sort of a one-step remove. But there's two big things that I wanted to talk about tonight, and that was our connections with the LISGO immersion through the New Zealand Gravity Group, and also Auckland's connection with Vera Rubin Observatory, which is managed through the well, it's going to be a national connection, but managed through the University of Auckland. And both of those things are big science projects, and both of them are being run out of a little country. And I want to talk a little bit about our ambitions, what we're trying to do with them, what kind of questions we're trying to answer, and also how it is that we managed to make that happen. And so I guess just to start off with, how many is I'm going to close it, see if I can get. Where's the rest of Teams? Where's it gone? Hang on a second. I'm not a regular Teams user, so this is causing me a bit of grief. Here we go. So I guess the question is everyone in New Zealand who's a member of an astronomical society has probably gone outside at some point and kind of looked up into the sky and seen, a big band of light across the sky and seen that we live in the Milky Way Galaxy. And so, this is just the knowledge that we live in a galaxy, and that we're, that the sun is one of, billions or hundreds of billions of stars. I guess that's knowledge that goes back certainly to the 19th century and arguably as far as Galileo and Giordano Bruno. But the kind of overall structure of the galaxy, that we live in a spiral galaxy, that it's got this kind of dense center, and we're somewhat displaced from the dense center. That's something that was really only figured out in detail in the 1920s. And so, it's kind of this feels like a kind of bedrock part of not just the universe itself, but our picture of the universe. And yet it's something that's, there are people alive today who were born, before this knowledge was gained by human beings. And in particular, at the beginning of the 1920s, there were two different pictures of cosmology that one could imagine having. And one picture of cosmology said that at that point we'd figured out that we lived in an island of stars, this Milky Way galaxy. It was only somewhat later that we figured out that we weren't living in the center of that island of stars. But it would be perfectly reasonable to think that this island of stars was one central island of stars that lived in an otherwise kind of infinite and empty universe. And the other picture, of course, is, and the picture that we now know to be true, is that our galaxy is one of many galaxies in the universe. So I can show you this image here, and it's not actually a picture of the Milky Way. It's a picture of another spiral galaxy, which is taken by the Hubble Space Telescope. And it looks pretty much like the Milky Way. It would be a close cousin of the Milky Way, but it's, tens of millions of light years off in some direction or other. And what I've done is I've just marked the position of the sun, or the analogous position of the sun as we would be in this galaxy. And you know, so the Hitchhiker's Guide to the Galaxy quote about how we live, you know, on an ordinary-looking planet around a regular star, in a, you know, an unfashionable spiral arm of the Milky Way Galaxy. That may or may not be true, but it certainly captures the sense that you know, we live in a galaxy. You know, we're one of many stars that live in the galaxy, and our galaxy is one of many galaxies that live in the universe. But that's like a huge change in our perception of the way that space is. And I must admit, how many people here, and I'll see if I can flip back to the Teams thing, see if we can do this. How many people here have seen the movie Moana? Yeah, the hands up. I will try and make it as interactive as possible. A reasonable number. So those of you who have not seen the movie and care about the plot, I will warn you that there's a spoiler coming. And the spoiler coming is this. So part of the key you know, revelation for Moana at the beginning of the movie is that she lives on this, you know, this single island in this giant and apparently empty ocean. And she's kind of bored of her little island. And then she finds out that her people are voyaging people. And that they came to the island in boats, and that they'd kept the boats, and that they were able to travel to the other islands that live in this kind of vast, you know, landscape of little islands dotted around the ocean. And in some ways, you know, obviously we can't travel other than in our minds to distant galaxies, but we can certainly think about what they look like. And so the kind of mental switch up that happened in the 1920s, that the Milky Way Galaxy was one galaxy among many in the universe. In fact, there's roughly as many galaxies in the universe, or the piece of the universe that we can see in the visible universe, as there are stars in the Milky Way, maybe, you know, to within a factor of 10. So, you know, like for every sun, every star we see in the sky, that's a you know, place where planets can live. For every star that we see in the Milky Way Galaxy, it turns out there's another galaxy full of just as many stars, potentially somewhere else in the universe. And so we have this, you know, massive expansion of our understanding of cosmology. And at the same time, we also have questions, or we can start to ask questions about where did it all come from and how did it get there. And so for me, as a cosmologist, it's not enough to just know that the universe begins, hang on a minute, that's not the right one, that the universe begins with a Big Bang. And that it's been expanding. What we really want to know is, how did everything that we see today, how did all of that stuff come to be? And so when we look into the sky, what we're really trying to do is to build up the story of what happens in the universe from the Big Bang through to the present day. And so one of the things that we know about the universe is that everything that we see in the sky, essentially every structure, everything that has component parts, cannot have existed, you know, as a bound object when the universe began. The universe was much too hot and much too dense for any solid objects to be able, or, you know, bound objects to be able to hold together. And so that's not just stars and planets, that's galaxies, but it's even atoms and the nuclei at the center of atoms, and the protons and the neutrons in the center of those, you know, those nuclei are made out of. All of those things will melt when they get hot enough. And the early universe was as hot and as dense as anything that we know has ever existed. So the part of the story that we want to be able to tell is, when did the first galaxies, you know, when did the first the protons and neutrons, the nuclei at the centers of atoms, the atoms themselves, the planets, the stars, you know, when did those things form? How did they form as the universe progresses? And what we learn, or what we've learned already, is that, in fact, a galaxy like ours is not, you know, even though this is kind of big and imposing galaxy, it's not actually the first thing to form inside of the universe. What we actually find out is that our galaxy is, or that the first galaxies to form appear to be small galaxies, and in big galaxies like ours are formed not just kind of out of stuff, you know, collapsing in the early universe, but they're formed as a result of the mergers of small galaxies. And so that's, we'd like to think of the biggest, they might think that the biggest things, like trees or something, and that the biggest trees were also the oldest trees, and the biggest whales are the oldest whales. But in fact, that for the galaxies, that's kind of the opposite. It seems that, in fact, in many cases, the biggest galaxies are probably the youngest galaxies. And so part of the story that we would like to, or the way that we would be able to check the story, is to be able to stretch our minds and our observations back into the past. And the one very cool thing about cosmology is that if we look far enough away from the Earth, we're also, because of the speed of light, we're also looking backwards in time. And so by looking at distant galaxies, whose light has been traveling towards us for half or 3/4 or 90% or even 95% of the age of the universe, we can see how the universe looked at times when it was much younger than it is today. And so this is something that's been going on for essentially as long as we've known that there are galaxies other than our own. Okay, any questions at that point, folks? People can feed them to the front of the room, or they can type them into the chat, or we can make this as exciting as we possibly can. Anything going? No? Well, good. Okay. Big pardon? I think if there are questions, they're going to have to be related to me.
Nothing at the moment.
Okay, cool. Okay, so the next thing we would like to do, or the thing that Lisa is going to do for us, this gravitational wave experiment, is the next thing I want to remind you of is that the center of our galaxy is a very weird and remarkable place. And so we're going to look towards the center of our galaxy, and when we do that, what we see is something that looks like this. So I'm going to play this, and hopefully this movie will work. Here we go, and I'm going to hit play. And so this region here is much less than an arc second on the sky. It's a region that's much less than a light year across. And what we're looking at here is the path of a single star that orbits around some dark but clearly incredibly massive point at the center of our galaxy. And so this is an animation, but it's an animation that shows the real position of the star as a function of time. And what we learn from looking at it is we learn that this thing at its maximum speed travels at around about, where are we? You got to time it just right, because it zips past around about 2.5% of the speed of light. So easily the fastest moving single star that we've ever seen. And whatever it's orbiting around, this little blob here is slightly off center. Whatever it's orbiting around is something that we can work out weighs about 4 million times the mass of the sun, and it's completely invisible. And so something that's completely invisible is black, and something that fits into a tiny space that still has a mass of 4 million times larger than the sun, we think the only thing that it can possibly be is a black hole. And so we think that big galaxies like ours, and most of the big galaxies that we've ever been able to observe, have supermassive black holes at the center of a galaxy. And unlike the kind of black holes that are produced when big stars die, which may be 10 or 20 times the mass of the sun, these things are millions of times larger than the mass of the sun. And it seems that they somehow form around, the process of the formation of these big black holes is somehow synergistic with the formation of the galaxies themselves. But the interesting thing is that our galaxy, our supermassive black hole, is not particularly special. All the big galaxies whose centers we've been able to probe appear to have these giant black holes at their center. And so this image here is from 2019, and it was the first image not of the central black hole itself at the center of the galaxy, but a region that's the central kind of donut hole here is about 6 times larger than the width of the black hole. And this particular galaxy is not our galaxy, it's Messier 87, a giant elliptical. You can read off the caption. It's about 55 million light years away from the Earth. It's a much bigger galaxy than the Milky Way. It's got a much bigger central black hole. It has a mass of about 1 billion solar masses, so about 1,000 times larger. And it was observed with a network of radio telescopes, one of which was located at the South Pole, others of them located in Europe, Hawaii, South America. His picture of the ALMA, the array of telescopes in Chile. And what they think they're observing is something that looks very much like the central object that we see and again, it's going to be kind of movie night, in the movie, now what is the name of the movie? I've gone blank. What's the name of the movie called where they go to the center of the black hole? Not Inception. What's the name of the movie, guys? Help me out here.
Interstellar.
Interstellar, exactly. It's on the tip of my tongue. And so we can model what we would expect to see if we were close to it. In fact, this was modeled for the movie Interstellar. And what we're seeing here is we're seeing this, this kind of circular disk of material that circles the black hole. The light that comes from the back of the disk is, kind of bent as it comes back over the top of the black hole. So we see this kind of distorted image. And if we play the movie here, you'll see that it's brighter in this direction as it comes towards us, darker in this direction as it's going away from us because of the so-called Doppler beaming that happens. These are complex spaces, and we can make sense of what we're seeing in these images by comparing them to these simulations. And again, it seems like there's just one black hole at the center of this galaxy, even though this galaxy we know must have formed as the result of the mergers of many, many, many galaxies. And just for completeness, here's an image of the Milky Way's black hole, and you can see that again it has this kind of frosted donut look, but for whatever reason it's got some additional bright spots that have been scattered around it. So the argument seems to be is that big galaxies like ours have just one black hole at the center, even though they're formed through a sequence of mergers, even though we would expect that the galaxies that formed them also had black holes of their own. And so the question that we're going to ask ourselves is, where do supermassive black holes come from? How do they get there in the first place? What happens to the central black holes when galaxies combine? And the hint here is that we don't see many galaxies with binary black holes. If we saw a whole cloud of black holes at the center of a big galaxy, we could think, well, it's the individual black holes that formed with each of the galaxies that contributed to this larger galaxy through mergers. But that doesn't seem to be the case. So it seems that these black holes have somehow found each other and merged together. And we know that that can happen because we've been watching that happen for the last, 6 or 7 years now, as the result of the work of the LIGO Observatory and joined more recently by the Virgo Observatory in Europe and Kagra in Japan. And there's also a gravitational wave detector in India that's in the process of being commissioned. So a network of gravitational wave detectors around the world. But in this case, this is something that, for someone like me, people had been talking about building LIGO pretty much since I was a PhD student. And it actually came online in 2015, or saw its first merger in 2015. But in fact, people had been talking about gravitational waves since the discovery of general relativity itself by Einstein in 1915. The first hint that gravitational waves might be a thing came in 1916. So it was almost 100 years between the idea of the possibility of gravitational waves through to the discovery of gravitational waves in the actual observation of them. And so LIGO, what LIGO sees is it sees the mergers of gravitational waves that are produced when mergers of black holes are produced by the endpoint of pairs of stars that have lived out their life as they orbit each other. They're particularly massive stars, so 10 or 20, 30, 40 solar masses, much bigger than the sun. They're born close enough together that eventually they spiral towards each other and merge into a single object. And so this is LIGO. Each of these arms is about 4 kilometers long. And I can't do the whole dance because I'm not there in person, but the way that this works is a gravitational wave that's coming towards this object from the sky will stretch one of the arms and will shrink the other arm at the same time. And so there's this kind of synchronized stretching and shrinking that happens in each of these arms. There are vacuum tubes in each of those pipes. You fire lasers down the tube to the mirrors at the end, and you use a big enough laser and you isolate everything well enough from the rest of the world. And it turns out that in those circumstances, you're able to measure a change in the length of the tube because of the passing gravitational wave, that is about 1 part in 10 to the 20. In other words, that's about 1 million times smaller than the size of the nucleus at the center of an atom that's sitting on the surface of the mirror. It's an amazing piece of engineering, and it's now one of 3 or 4 of these detectors that are active around the world. And the reason it happens this way is because 2 black holes that are approaching each other are essentially a giant cosmic egg beater that stirs up the fabric of space and time. And the reason we get gravitational waves is that Einstein tells us that gravity works by bending the fabric of space in some sense. But as an object moves through space, then the bending has to snap back. And anything that's capable of bending and then kind of snapping back afterwards, pretty much anything that you can squash and it will bounce back, you can propagate waves in a medium like that. Those waves, as the 2 black holes orbit each other, you're changing the shape of space-time, that propagates waves. Those waves carry away energy. We've got to pay for that energy somehow. The black holes pay for them by getting closer to each other. They orbit faster. They radiate more effectively. They get closer and closer. And we have this long phase called the in-spiral that ends very, very quickly right at the for the last few orbits. And it's in those last few orbits that we produce the most gravitational waves. And it's that point that we see the signals that LIGO produces. So this is the gravitational wave detector that we've already got. It's detecting black holes that are 10 times bigger than the sun, 20 times bigger than the sun, and it's been doing it on a fairly regular basis for the past 5 or 6 years. So here's a video of what happens. You see these 2 black holes merging. You can see the signal down the bottom. Again, if this was in person, I'd ask you to perform the signal. What we're seeing here, I hope this is coming through in the sound, is a signal that goes like whoop, and then it's cut off right at the end as the 2 black holes meet and merge. It's a signal that acoustic engineers call a chirp, something that's rising in both frequency, or in other words, in pitch, and volume at the same time. Almost all of the action happens right at the end of that signal. Okay, so that's LIGO. We've sort of got used to LIGO now. LIGO is not like a telescope in the sense that, an installation like LIGO is going to cost you the thick end of $1 billion. So it's not, you can't build a gravitational wave detector in your backyard. I mean, you can, but it won't be sensitive enough to see any known sources of gravitational waves in the universe, which is kind of sad. So, in gravitational waves, when a single black hole merges, that's suddenly the brightest, the loudest thing in the sky, and then the sky goes quiet again. LISA, on the other hand, is a somewhat different story. And so LISA is a European space mission led by the European Space Agency. It's €1.5 billion worth of spacecraft, so it will be expensive. It's slated for funding, so it's on the, it's now been funded, approved. It's on the pipeline towards construction, but that process could take most of the coming decade. It's not going to happen quicker. And so what it's going to look like is it's going to look something like this. This is a very sketchy picture. So the picture that we're meant to have here is that this is the Earth orbiting the sun. And LISA has arms about triangles, about 2.5 million kilometers on the side. And it orbits the Earth, I think, about 10 degrees behind the Earth, so quite a bit further than the Moon, but follows the Earth around the sun in its orbit. And it's 3 different spacecraft, each of which fly on their own. So 2.5 million kilometers, and that means that it's sensitive to very low frequencies. So LIGO is sensitive to signals in the hundreds of hertz range, so actually signals that are common to the human voice or music. That a lot of the audio signals are hundreds of hertz. So we're looking at millihertz through to 1/10 of the hertz, which means we're looking at much lower frequency signals. But if you have 2 galaxies that merge, and the big black holes at the center of those galaxies, they've got much further to go as they orbit each other, so they're going to orbit each other more slowly. So the gravitational waves that they produce is going to be at a much lower frequency. It's scheduled to the early 2030s, as I said, and it's a project being run by the European Space Agency and NASA. So anyone pretty much can join the LISA consortium. What it costs nothing to join, what it costs is our time. And so what we had to do to join was to convince them that we were able to make a useful contribution. Our time, in fact, is paid for by a significant grant from the Marsden Council, so $3 million over 3 years. And what it pays for is the students and postdocs that work on this project. And the reason we're doing this is it turns out that there's a bunch of people in New Zealand who can contribute to LISA's understanding LISA science in various ways. And so that obviously includes me, someone who thinks about the formation of the universe on large scale. So I'm interested in the process by which galaxies form. It includes, my colleague Jan Eldridge. And it turns out her interest in binary stars, even though I've been focused on the black hole story, the white dwarf binaries in our solar system are not going to merge for billions and billions of years. They move too slowly. But as they orbit each other, they're producing this steady rumble of gravitational waves that will be part of the signal that LISA picks up. And so we'll be able to see the white dwarf signal, or LISA will be able to see the signal in white dwarfs that comes from the white dwarf binaries in the Milky Way, and it'll be part of the signal that LISA detects. And so the better that we can understand the distribution of white dwarfs that we expect to see, the better we can understand the LISA signal that we're expecting LISA to produce. So what are we doing? What we want to learn is that when galaxies merge, then sooner or later their central supermassive black holes have to merge as well. And those mergers should be visible to LISA. In particular, it's a big problem to extract the signal. So LISA's going to pick up a signal from the way that the distance between these spacecraft change. It's going to track that with the lasers that are on board each of the spacecraft shining towards each other. But it's what we call the cocktail party problem, because LISA's going to see hundreds of the signals from hundreds of black holes or pairs of black holes that exist in the universe all at the same time. The mergers take months or years to proceed, so you're not going to see the single bright signal that you see with LIGO. You're going to hear this kind of steady rumble, and it's a little bit like pulling out each of the individual signals. It's going to be a little bit like being in a noisy room and trying to focus on one conversation, then another conversation, then another conversation. And to do that, you need fancy statistics. And it turns out we also have some very fancy statisticians in New Zealand who actually for a very long time have been contributing to the analysis of gravitational wave data. In particular, my colleague Renata Meyer at the University of Auckland, who's a professor in the statistics department. And so what we get is something like this. It chases these satellites chase the Earth, as I said. And you can see that this orbit is cunningly constructed so that each of them are in their own orbit, but they're designed so that they track, they'll maintain this kind of triangle shape as they orbit. But because these signals are visible for months at a time, one of the things that we're going to have to account for is the fact that LISA is moving substantially in its orbit, and the way that you pick up a gravitational wave signal is going to depend very much on your orientation with respect to the source. So all of these things are going to have to be accounted for and made sense of as LISA moves around the sun. So this is astronomy, Jim, but not as we know it. It's only possible with a big team and lots of money. But the interesting thing is we don't have to put in any money at all. The cost of the LISA mission has been covered by somebody else. Gravitational wave detection is super hard. Just a huge amount of subtle work has gone into the design and construction of the LISA mission. And to give you one taste of the kind of problem that you deal with is that in order for the math to work out right, you're assuming that the spacecraft are following perfect orbits around the sun. But they're not going to be following absolutely perfect orbits because the sun will shine on one side of them, but not so much on the other side, and that's going to give them a little push. They'll bump into dust and schmutz that exists in the solar system. And as they do that, that is obviously going to push the spacecraft off course a little bit. And so what the LISA spacecraft will have is they'll have these central masses that are flying freely around the sun. And the rest of the spacecraft has actually got tiny little thrusters that will be designed to keep the rest of the spacecraft oriented towards the central freely falling mass. And just developing that technology has been a story in itself. It answers questions about how and why. So, how did the universe begin? How did the galaxies form? Why do things look the way they do? And not just what. So I could have given this pretty much as a physics talk. But what it's actually going to reveal is the global history of the universe. When did the first galaxies form? When did the first mergers form? How long after the merger of a galaxy do we see the mergers of black holes? What happens when multiple galaxies, merge at the same time? All of these things are questions that we would like to ask, and we can hopefully answer with the LISA mission. So that. But wait, there's more. But I'm going to take a pause here and just check to see whether there's any questions that are coming from the room here. I realise this is a slightly unfriendly.
I have a question, Richard. The idea with LISA, the way they keep the orientation, is that similar to what was used with Gravity Probe B, where the spacecraft was actually isolated from the apparatus? So that any effects on the spacecraft, it would keep recentering on the apparatus.
I believe so, and also there was a mission flown called the LISA Pathfinder mission that explicitly tested the technology that LISA is going to use to do this. And in fact, one of the reasons why the idea of the LISA mission is already 20 years old, and one of the reasons why it hasn't been done is because people realized that the technology was sufficiently hard that it would require, like a technology demonstrator mission to fly. And so, that was done better part of 10 years ago now. But yes, it's a similar technology as I understand it. But I'm the Gravity Probe B. I mean, it's a while since I looked at that in detail, but I believe that the answer to that is yes.
Well, the other question I had in your diagram showing the 3 satellites orbiting the sun, so the orientation does change as they orbiting the orientation of the triangle. So
it does, absolutely.
The direction of sensitivity for incoming gravitational waves, is that how it works?
In principle, if you've got a steady source, like a nearby pair of binary white dwarf system, for instance, which some of these you'll be able to resolve the individual sources. Pull those out of the background. The fact that it changes as a function of time, or the sensitivity to that source changes as a function of time, means that you probably stand a pretty good chance of being able to recover the location of that object in space, from the way that the sensitivity changes. But yeah, absolutely, that's something that you've got to factor into it. So LIGO, the signals are typically seconds long or less. And so the configuration of the LIGO detectors doesn't change very much, during the course of a single signal, whereas the configuration of the LISA detector can change quite a bit. Any further questions about that? There's one more thing that I want to tell you about, and that is the LSST. And so this is so it started out being called the Large Synoptic Survey Telescope. This was something that was proposed or been thought about up until 2010 in the United States. And it's recently been renamed the Vera Rubin Observatory in the honor of Vera Rubin, who was one of the first people to figure out in detail the properties of dark matter. And in order to keep the acronym, they've renamed what it's going to do the Legacy Survey of Space and Time, LSST. And what it's going to do is the object that will do that is this telescope here. So this is a much more familiar device to an amateur astronomer. It's an optical telescope. It's built in the mountaintop in Chile. It's a very big optical telescope. It's got an 8-meter mirror. So large, but not completely record setting. And when it's finished, it's going to look close to being finished now. It's going to look something like this. What it is going to do is it is going to take a picture of the southern sky, essentially, every 4 days. And the way it does that is it points, for every pointing, in 15 seconds, it can see about halfway to the edge of the universe. Each of the pointings that it takes is about, so let's see how many moons across. So it's about 4 degrees in this direction, about 4 degrees in this direction. So a little bit less than that, about, I think about 50 full moons. So it images a very big patch of the sky, and it does it 15 seconds. It has a series of filters that it cycles through. Then it moves to the next patch of the sky and repeats the process. And so in order to do that, it uses a digital camera that looks like this. So this looks very much like what you would strap to the front of your SLR, except you can see from the size of these stairs that this is, in fact, the world's largest camera. It's multiple gigapixels. And it's designed that it will run the survey will run for approximately 10 years. And so the way that this works is that you wind up getting images of everything from Earth-crossing space rocks through to the distant supernovae. You're also going to get images, unfortunately, of an awful lot of Mr. Musk's Starlink satellites, which is not making him popular with my colleagues. But you're going to get, it's a single survey that is sensitive to a vast range of interesting objects. And so how are we involved? So we're involved again as an international collaboration. In this case, New Zealand is required to make an in-kind contribution. In other words, to provide services and access to data that will be of value to the project. So we can provide, in collaboration with our colleagues at Canterbury, follow-up time on telescopes at Mount John, and access to the MOA archive, to the archive of images taken as part of the ongoing microlensing survey. So that means that we are able to go fishing in this river of data. The total direct cost, the real money cost of this over 10 years, is well under $1 million. And when I say under $1 million, I mean a few $100,000. But again, it buys us into $1 billion project. So these two things are things that are allowing us to do big science in a little country. And so what are we going to learn from this? We're learning that we absolutely can do big science from New Zealand. A lot of times teams need big people, and we have great people, so we're able to get inside these collaborations. We're doing it on the smell of an oily rag, and we're doing a fair bit of nimble footwork in order to make it work. If you're talking to someone, cynic, no one funds fundamental science for fun. They do it because they think there are advantages to the countries that do it. But other countries do fund it, and we don't. So there should be a clearer case for building this kind of activity here. And we would very much like to be, engaged in more cleanly articulating that to our communities. I just want to mention at the end, there are other people in New Zealand, other collaborations that we're involved with. I've focused on the two that touch the University of Auckland. But the IceCube collaboration, for instance, that Jenny Adams has been working in for 20 years at the University of Canterbury, that's instrumented a cubic kilometre of ice at the South Pole to detect interactions with neutrinos and cosmic rays. We're involved in a variety of upcoming space missions, WFIRST, or now the Nancy Roman Observatory, in various ways. And, we do Scott Base, obviously, which is, hundreds of millions of dollars. So it's not like we can't find the money for some things. And, last but not least, colleagues of mine at Auckland and also at Canterbury are involved working on the Large Hadron Collider and contributing to that in various ways, and also helping technology from that flow back to New Zealand. So I'm going to end here. So I've it's because it's an online talk, I've kept things a little tighter than I might otherwise have done, and I've hopefully left enough time to take a reasonable number of questions at the end of it. So let me end my screen share. Hang on a minute. Back here, Mr. Gates. Here we go. Nope. Stop sharing. Here we go. Cool. So yeah, questions, thoughts, consequences.
Sorry.
Richard, is there anybody in New Zealand working with the LIGO or Virgo Collaboration?
Yes, yes. In fact, there is. Some of my colleagues in statistics involved indirectly in that they've developed algorithms that are used, and we're actually, I think I can say this without giving up too much away. We are hoping that that some of us at least, or some of my colleagues at least, will become formally members of the Ligo Collaboration, which means that they have access to data. But Renata in particular, over the last 20 years has been developing statistical algorithms that are heavily used by LIGO. So we actually have quite tight connections into the LIGO data as a result of that. So the answer is yes, and it's something we'd like to build more of as we move on.
Thanks.
Just a really basic question. Did you say that there's only one black hole known to be at the center of the Milky Way?
Yes. Yes, that's exactly what I said. And we know that because we can...
Are there other black holes that are not in the center?
So we know of plenty of black holes in the Milky Way that are associated with stellar remnants. So that Cygnus X1, that has a mass of maybe 10 times the mass of the sun. We see plenty of evidence, typically because they're in binary systems traveling around stars, and so we see X-ray emission from their accretion disks, for instance. So there's good evidence for the existence of black holes in the Milky Way that aren't, a reasonable number of them. But there's only one supermassive black hole, so something that weighs millions of times the mass of the sun rather than 10, 20 times the mass of the sun at the center of the Milky Way. And because we can see, both from radio images of the central region of the black hole, and because we can watch the motion of stars as they interact with this black hole at just ridiculous speeds, if there was another supermassive black hole near the center of the Milky Way, it would give itself away, and it's clearly not there. So the rule seems to be one big black hole per galaxy. And we're able to observe that not just in our own galaxy, but in others. There are examples with binary black holes, but they seem to be the exception rather than the norm.
I've got a question about that, Richard. Is there any understanding of why they would merge so frequently?
Well, it's actually that's what we'd like to do. In principle, as the two galaxies merge, you can simulate what happens, and the black holes, one black hole will come in with some speed relative to the other. They're both moving through material, and so they're kind of throwing material. Like if you throw a black hole through a cloud of stars, it's almost certainly not going to bang into any of them. The cloud is mostly empty space. But as it moves through the cloud, it kind of throws stars around with its gravitational field, which causes it to slow down, what we call dynamical friction. And so this is, it's a problem you could have worked out a couple of hundred years ago if you were sufficiently well motivated. There's nothing mysterious about it. And so the question is like one of the questions is, how efficient are these processes? So, how long does it take after two galaxies merge for their central black holes to find each other? And it is actually a big challenge to. We have pretty good reason for believing that the mergers take place because nearby galaxies only have one black hole. But if they aren't efficient, you could easily imagine that if you do the calculations, a lot of times it seems like it would take longer than the present age of the universe for the galaxies to actually find each other, or the black holes to find each other and merge. And so it's actually a big, like for a variety of reasons, we think that those mergers happen quite quickly. But we're also trying to make sense of what we see, and then that actually working out that timescale in detail is in fact pretty much what my group is working on, or aspects of that. So yeah, you've just asked an absolute live question in astrophysics.
Any other questions from the audience?
Just a basic question. So, what is the lifespan of a black hole, Rich? Do we know that or not? The lifespan of a black hole?
In terms of any relevant. Sorry, what was that?
Lifespan of a black hole. I guess he's talking about orbiting radiation.
Yeah. So the claim is that if you just know about kind of classical physics, general relativity and Newtonian mechanics, you'd think that a black hole lasted forever because it looks like nothing can get out of them. But we actually know they do, or we believe they do slowly leak energy, essentially because of quantum mechanics, this process called Hawking radiation. And so the interesting thing is that the smaller the black hole is, the faster it leaks energy, which means that a big black hole that weighs, solar masses or millions of solar masses, it will have a lifetime on the order of trillions of years, many, many, many tens of times, thousands of times longer than the present age of the universe. So to all intents and purposes, it seems that as far as we're concerned, black holes last an infinite amount of time because we don't live for trillions of years. There are theories that allow for the possibility of black holes being formed in the very early universe that could potentially have much smaller masses than stars or even planets. And so in the present day universe, we don't, we can calculate how big a black hole with the mass of the Earth would be, but we can't imagine any process that would take, an Earth amount of mass and squash it into a black hole. So we think that the smallest black holes that are produced in the universe, from, sort of a few minutes after the Big Bang onwards, must be, 5 or 6 times more massive than the sun, just because we can't see any process that makes a smaller black hole than that. But if you were to find one of these little guys, then you would be potentially seeing something weird that had happened in the early universe. There's no reason for the universe to do that. So if you did see that, you'd be seeing something unexpected. You'd definitely be on an airplane to Stockholm to pick up your Nobel Prize pretty shortly after that happened. But the key thing from from that point of view is that those little black hole that has a mass about the same as a mountain has a lifetime that is about the same age as the universe, so 10 billion years. A much smaller black hole, one that weighs a few kilograms, that'll be done and dusted in a tiny fraction of a second. And so one of the ways that you would go looking for these black holes is actually they'll be glowing. There's some tiny point that's glowing in space, for no good reason, and getting brighter and brighter as it loses mass and therefore heats up. It gets it loses mass more quickly, and eventually evaporates in a puff of gamma rays. So in principle, we can go and look for those. In practice, we've never ever found them, or even anything that looks much like one. But yeah, it's a long answer to a short question, and it's an interesting question.
Thank you.
I had a question to do with the money side of this. That presumably there would be a big requirement for IT resources for processing all the data coming out of these projects. When, like the Vera Rubin Observatory is imaging the whole southern sky every 4 or 5 nights, you're going to have a huge amount of data to sift through and store.
So the Vera Rubin Observatory absolutely does. It's a big data project in some sense. It's going to have, I don't know, 100 petabytes of images or something like that when it's done. And so there's a huge compute component to that project. And because we're contributing to that project, we get access to those computing resources. In the case of LISA, because the signal that it's seeing is only measured in hertz, the actual data stream from LISA would fit over 10 years will fit on a hard drive. The expensive part of measuring LISA is not so much the data itself or the computationally expensive, is like the models that you might want to fit the LISA data to are extremely complex, and so each time it's got hundreds of variable parameters. And if you want to improve the fit to those models, then you've got to adjust each of those parameters every time you do it, and that could very quickly get very expensive. And so we have access to the supercomputing facilities that are maintained by NESI in New Zealand, which is something that we make a lot of use of. We also have access to facilities with collaborators in Europe that we use quite a bit.
I have a question from the internet from Stephen Grace. He wants to know if anybody in New Zealand is still involved in the SKA.
That's a good question. I don't exactly know the answer to that. my understanding, I mean, certainly the government decided not to get involved with it or not to stay involved with it. There was a suggestion that, and this is, I don't know how much I can say because some of this is kind of scuttlebutt. There was a suggestion that an individual institution in New Zealand was trying to negotiate with them, as a university rather than as a country, which originally we were told was not possible, but sort of became possible. It appeared. But that university has recently announced that it's closing down its radio observatory. So I don't have a huge amount of information on that. I think it is very likely that some individuals who are working in New Zealand will continue to be quite closely involved with the SKA. The situation here was a complex one. And there's certainly no reason why we can't be, but there's no national involvement. And my colleagues at Victoria, for instance, two good radio astronomers there. I imagine that they'll try to stay connected if they can.
Any more questions from
I mean, it is. I guess one other thing I would say is that, the New Zealand was looking to spend somewhere between, numbers vary, but, $30 million to get involved with the SKA. And then, more money on top of that. Was never quite clear how much. So the science, the projects that we're talking about here are similar in scope and ambition. But the direct cost to the country is much, much smaller.
Any more questions online or from the audience? So in that case, I'd like to sort of thank Professor Easther for doing this talk for us. Really appreciate it.